Let's look at the term-term correlation calculations. The basic ones are calculated, the basic version of that is in TT1 and TT2. If you go into index.script, you'll see in tt1.mumps down here is where it runs. And there it is. tt1.mumps, it works on a copy of the database. It's a read-only version of mumps. It doesn't alter the database. It writes out to standard output, which goes to sort, which goes to unique-c, which means unique will count, and it's written out to a file ttsorted.temp. And it runs in the background. The ampersand means it runs while other things are going on. It's part of our parallel processing routine here. We capture the process ID. That'll be used later. But in this case here, I simply waited and exited because I just wanted to stop at that point. So I've already run this on 1,000 documents. So let's look at tt1.mumps first of all. Okay, there it is, pretty small. Notice it uses the read-only database at the top here. It checks to see if you gave it the database. It establishes the database that's unique to my version of mumps. Now, what's it going to do? It's going to go through each document and find the words that co-occur in the document. So we have, this is again my modified version of a for loop. We go through each document, we get those values of D, all the values of D for all the documents. For every value of D in up arrow doc, we'll get it as D. We then enter a block. For a given D, we find all the W, all the words W that are in document D. Now we want to find the other words in the document D. So we set W1 equal to W. And then, this is a more complicated for statement, it's more traditional. Forever, notice there's two blanks, we set W1 equal to the next word relative to W1. Well, the first time in, W1 is the first candidate word, and we will get the next ascendant adjacent word to it. Subsequently, we'll get additional words until we run out of words. If we do run out of words, we quit. Notice if W1 comes back as empty, we quit. Notice there's two blanks after the quit. We enter the block here. Actually, this could have been done on the same line, but whatever. We write out word W, a blank, and word W1. So what this is doing is it is writing out those pairs of words that co-occur together with one another in a document. When we go through all the documents, we look for all the co-occurrences. Notice, however, that I am not starting with the first word in each document for the second word of the pair. Notice down here I set W1 equal to W, and I advance from that point. Because quite simply, if I've got, say I've got a document that has a word aardvark and it has a word banana, and I start off with aardvark, and the first word I'll get is banana, and I'll count the number of, and that'll count as co-occurrences. There's no need when I get to banana to start with aardvark, because we already have done that. We have already determined that they co-occur. What we're really calculating here is a diagonal matrix. The upper and lower diagonals are identical. So to save time, we only do it forward from the first candidate word, from W. W1 will be those words which are alphabetically higher than W. We can reconstruct the term-term matrix, the other diagonal, later. It's much quicker to do it later on. So I will get, for each time two words occur together with one another in a document, I'll get a line in the output. It'll have the first word, blank, and then the second word and a new line character. And I'll write these all out. Now when I do that, let's run it, because I can run it right here. tt1.mumps. Let's run it past more because it'll flash by quickly. Whoops, forgot the database. Copy one, that's one of the databases. And you see those are the words. You can see like acetaldehyde, and it goes, you see all the words higher than it alphabetically as it's chugging along. There's lots of them. As a matter of fact, let's count them. Instead of going to more, let's go to WC. Let's take a moment because it has to go through the entire collection. I think it's around just under 700,000, something like that, pairs of words for the first 1,000 documents in the collection. Yeah, 636,000 pairs. Okay. Now what I want to do is count them. I want to know for word A and word B how many times they co-occur. Okay, that's the real thing we're looking for here. So if I go back here and I run this to sort, what's going to happen? Well, all of the word pairs that are the same are going to come out adjacent to one another in the file. So in one document we had word A and word B, and in some other document we had word A and word B, and some other document we had word A and word B. When we sort it all together, we're going to get 3 lines with A and B on them right next to one another. So let's sort them and run them past more and see what it looks like. Again, this is going to take, everything has to be calculated before the sort finishes. This is not, we have to wait until it's done, in other words. It's not real time. And you can see there, abdomen occurs with analysis 4 times. There are 4 separate instances of abdomen and analysis in the output file. That's good. I won't go any further than that. Because next of all, we want to count them. Unique -C is how we count them. And again, I'll push it into more. And have to wait for it entirely to complete. That's why I'm using a relatively small count of 1,000 documents. It would take too long to be running 10, 20, 30,000 documents. And there you can see, there it is right there, 4 for abdomen and analysis. And the count, that's the first thing that occurs after unique. It gives us the count of the number of times the words occur together. They don't occur terribly often together because it is a small sample size. I could actually find out how often they occur. This is as far as what you see on screen right now as it goes in the actual text, but this is where we write it out to a file. But if I ran it to sort again, -NR, and then to more, what that does is it does a numeric sort on the first field. You didn't specify anything other, so it goes to the first field, first key, that's the number. And R means reversed order. So instead of getting the lowest to highest, I'm getting highest to lowest. And as it turns out that truncate and word co-occur with one another 35 times. So does abstract and word, and abstract and truncate, and so forth. These are the frequencies. They're not very high. Again, it's a small sample size. If I let it spin down here, you can see that there's a broad plateau of relatively small counts there. 4 looks like it's got a lot. When do we get to 3? There's 3. Okay, so that's what we get. We get that. So we're ending up with a file that's going to that is going to have the count, the number of times the words co-occur with one another. That's what we're really looking for. That's our raw data for the term-term correlation matrix. Later on, once it's done, there is a program called tt2.mumps. index.script/tt2.mumps. And here it is. tt2.mumps takes a parameter which is the minimum threshold. What is our minimum threshold for words to co-occur? They're below that threshold, we ignore them. You know, there's a bottom line. The input is the file that came from tt1 up above, and then we just sort them numerically and into a term-terms matrix sorted .text so that we can look at them, and they're sorted by their numeric value that comes out of here. We're actually going to calculate something in tt1, which is we'll see in a second. So let's bring up tt2, tt2.mumps. Okay, it removes any previous instances of the term-term correlation matrix, up arrow tt, checks to see if you've given it a parameter. The parameter is going to be the minimum value. It sets it to %1, that is the parameter. It then says if you didn't give it a parameter, the parameter is empty, you get it sets it to 5. But since you had to give it a parameter, it's probably not empty. Anyway, it doesn't check to see if it's numeric. That could be a problem, but hopefully it's not. All right, we are basically, now what does the program do? It reads in a line. Remember, it's reading in from standard input. The line consists of a number, a lot of blanks, a number, a word, blank, and a word. Well, first of all, if we run out of input, we're done. We want to get rid of all those extraneous blanks. We're going to use $piece to break things up, and we don't need a whole bunch of extra blanks. Unique puts a whole lot of extra blanks at the beginning. So zblanks, my function, removes blanks, extraneous blanks. Duplicate blanks are replaced by a single blank. All right, so then I can pull off the words. Word 1 is the second piece. The first piece will be the count. Second piece will be word 1. Third piece will be word 2. So I get word 1, word 2. And then I pull a fast one here. I don't use $piece. I set CO, that's going to be the count, equal to +A. A is the input line. Well, that actually turns out in my version of mumps to be a little bit quicker. The plus operator is a unary plus. It doesn't really do anything, but it forces a numeric interpretation on the variable a. That means the numeric part, which is at the beginning, that'll be kept. Anything after that, the blanks and the words, they'll be dropped, because it only processes, if you remember from mumps, if I have 123 Elm Street and I say and I do arithmetic on it, it'll only look at the 123 part. So that basically, it's quicker than doing a $sign piece. $sign piece involves a lot of pattern matching, and whereas this just checks to see if there's something non-numeric, and then that's when it terminates. All right, if then we check to see if the value, this would be the number of times these two words co-occur, is less than our minimum. The minimum was a parameter. If it does, we loop. We read the next line. We ignore it. Otherwise, here we calculate TT on word 1 and word 2 is equal. The justify just makes it so I don't get a lot of trailing decimal fractions. These are not all that precise a calculation, so we don't want 15 digits of accuracy. 3 is fine. Now, notice the 1 down here, 1 comma 3. 1 is obviously insufficient as a field width, and when the field width is insufficient, it ignores it and it just uses what it needs. The 3, however, is the number of digits to the right of the decimal point. That it keeps. And what it does is it basically is going to calculate a ratio here. The count divided by this expression, which is the sum of the number of documents in which word 1 occurs plus the number of documents in which word 2 occurs minus the co-occurrence. So let's look at the situation where word 1 and word 2 both occur in 10 documents, and they co-occur together 10 times. That means the value of this will be 1. They obviously are co-occurring in every document in which they exist. They couldn't be any other result there. If, however, word 1 occurs in 100 documents, word 2 occurs in 10 documents, and they co-occur 10 times, well, it's going to give you a completely different value, a much lower value. It's going to be 10 over 90. Going to be 1/9, because there's an awful lot of possible co-occurrences that didn't occur. Because word 1 occurred in 100 documents. There's 90 documents in which word 2 did not occur. So this is due to Salton. It's a pretty good calculation of the relative strength of the co-occurrence. So that's TT1. That's TT of word 1 versus word 2. Notice what I do here. I just reverse it. I word 2, comma word 1. This gives us the other diagonal matrix. Instead of doing it up above and doubling the size of all the files, we do it here. Then I write it out. I write out the value, I write out the words, I write out the frequency of co-occurrence, I write out all the parameters here, the number of times word 1 occurs in, a number of documents it occurs in, number of documents word 2 occurs in, and this will go to output. Now let's see if I can get this all together and running. Okay, there is tt1.mumps, and that's where its output goes to. And if I do tt2.mumps, and I give it a count, let's put 3 as a minimum here. It might be a little, I don't know, 3, 4. I don't know if it was less than 4 or if it was 4 or less. Let's put 4 and see what happens. And the output here is simply, I could sort it, but let's just go to more and see what we get. Now this is going to take longer. This is basically chaining them together. All right, there they are. And you can see, well, let's take the highest ranking one I can see down here, which would be abdominal pain. Gee, those are good words. I mean, when you think about it, abdominal pain is a common phrase. There's the document counts and the co-occurrences. That's neat. Let's sort them. Let's run this thing. Instead of going through more, let's go sort -n and go to more. Oops, NR. Let's go to NR because I want to see the most occurring, the highest ranking at first. You see what I've done here? I'm running tt1.mumps on copy 1 of the database. Its output is going to sort. Its output is going to unique-c. Its output is going to the input of tt2.mumps. Its output, if I spell sort correctly, is going to sort numeric reversed order. The first key on each line is a number. And then it's going to more, which just gives it to me page by page. Crossing my fingers, I hit enter. And we should see them ranked now with the most frequently co-occurring words based on that metric appearing at the top. Now we are doing more work here because we've got an extra sort going on. There we go. IGF-I, which is an insulin, which is a form of insulin, and insulin-like. They occur in 4 documents. Each of them occurs in 4 documents, and they co-occur at 4, so they get a 1. Expiratory force, they assume that's got something to do with pulmonology. Aureus staphylococcus. Well, it's actually, the phrase is actually Staphylococcus aureus. But yeah, that's these are words that do in fact do magnetic resonance. That's a common term in medicine. Your MRI scan is actually a magnetic resonance imaging scan. So yes, these are the most frequent. These are the ones that are most tightly linked together. Now there was a lower threshold, of course. There could have been some words that occurred in 3 documents each, and they co-occurred 3 times, which would also give me a 1. But it would be a relatively small number. So anyway, as we go down the list, eventually we're going to need a cutoff as to what we consider significant. Now we're going to look at some other ways of calculating term-term correlations, but this is the basic way, and it actually works.